微软研究人员推出 MatterGen 材料发现的新范式。2025年1月16日，微软研究团队正式发布了 MatterGen， 一个基于生成性人工智能的新模型，旨在推动材料科学的发展，尤其是在高效太阳能电池和二氧化碳回收等领域的应用。MatterGen 的出现标志着材料设计领域的一次重大革命，其核心理念是利用智能算法超越传统的试错实验方法，加速新材料的发现与开发。MatterGen 的技术背景与功能。MatterGen 的设计理念在于通过分析海量的数据来识别潜在的新材料。该模型结合了先进的机器学习技术和数据挖掘方法，使研究人员能够从已知材料的性质中提取出有价值的信息。这一过程不仅提高了材料研发的效率，还能够根据具体的应用需求进行材料的个性化定制。例如，在高效太阳能电池的开发中， MatterGen 能够根据不同的光电转化效率需求，快速筛选出适合的半导体材料；而在二氧化碳回收的研究中，模型则能推荐出具有最佳吸附性能的材料组合。这种智能化的材料发现方式，使得研究人员能够在更短的时间内获得更具前景的材料候选者，显著缩短了研发周期。发布活动与公众反响。 MatterGen 的发布活动通过多种渠道进行了广泛传播，包括社交媒体、视频分享平台以及微软官方网站。微软研究团队的成员，特别是参与该项目的 Tian Xia 和 Zhihan Lu， 积极分享了他们的研究成果，吸引了大量科研人员和公众的关注。发布当日，相关视频在 Facebook 和 Twitter 上的观看次数迅速攀升，显示出公众对这一新技术的浓厚兴趣。在 Facebook 上，微软研究团队发布了 MatterGen 的介绍视频，迅速获得了近9000次观看。观众们在评论区积极讨论这一创新技术的潜力。一些观众表示， MatterGen 可能会在未来的材料科学研究中发挥重要作用，特别是在应对气候变化和能源危机方面。MatterGen 的意义与未来展望。 MatterGen 的推出不仅为材料科学领域带来了新的希望，也为实际应用提供了新的可能性。生成性 AI 在材料发现中的应用可能会彻底改变传统的研发模式。通过数据驱动的方式，研究人员可以更加高效地探索新材料，减少资源浪费，提升研发成功的概率。随着 MatterGen 的不断优化和应用，未来可能会在多个领域实现突破。例如，在可再生能源方面， MatterGen 可能帮助设计出更高效的光伏材料，推动太阳能技术的进一步发展。在环境保护方面，模型能助力开发出新型的二氧化碳补给材料，对抗全球变暖。总结， MatterGen 的推出代表了材料科学研究的一次重大飞跃。通过集成生成性人工智能技术，研究人员将能够在更短的时间内发现和开发出符合特定需求的新材料。这不仅将对能源、环境等领域产生深远的影响，也为科学研究的进步提供了新的动力。微软研究团队的努力将推动材料科学走向一个更加智能和高效的新时代。
The introduction of MatterGen by Microsoft researchers represents a significant shift in the materials discovery process, leveraging generative AI to move beyond traditional trial and error methods. Here are some counterintuitive insights related to this development. 1. AI versus human ingenuity. While generative AI models like MatterGen are designed to enhance the speed and efficiency of material discovery, one might intuitively think that they could replace human researchers entirely. However, the reality is that these models serve as tools to augment human creativity and decision-making rather than to replace them. The human element remains crucial for interpreting results, making informed decisions, and guiding the direction of research. 2. Data overload versus insight generation. Another common assumption might be that more data always leads to better insights. MatterGen challenges this idea by demonstrating that the quality of data and the algorithms used to interpret it can be more important than sheer volume. The model effectively filters and analyzes vast datasets to extract relevant information, highlighting that the right tools can turn potential data overload into actionable insights. 3. Trial and error still relevant. The notion that trial and error methods are obsolete due to advancements in AI might seem convincing. However, MatterGen does not eliminate the trial and error process, instead it refines it. The model can predict potential materials that are worth testing, thus making the trial and error phase more targeted and efficient rather than entirely removing it from the equation. For material customization, a common belief is that creating highly specialized materials requires extensive and often impractical experimentation. MatterGen's approach illustrates that customization can be achieved through computational methods, allowing researchers to design materials tailored to specific applications, such as efficient solar cells or CO2 recycling, more economically and quickly than traditional methods would allow. 5. Public perception of AI in science. The excitement and widespread attention generated by MatterGen may lead one to believe that the public fully understands and supports the use of AI in scientific research. However, there is often a gap between technological advancement and public comprehension or acceptance. The nuanced implications of AI in materials science, such as ethical considerations and the potential for job displacement, may be overlooked in the initial wave of enthusiasm. 6. Efficiency versus innovation. It could be assumed that increasing efficiency in material discovery would stifle innovation since processes become more streamlined and predictable. However, MatterGen's ability to rapidly iterate through potential materials may actually foster greater innovation by freeing researchers from the constraints of traditional methods, allowing them to explore more radical or unconventional ideas in material design. 7. Interdisciplinary collaboration. The development of MatterGen may suggest a more isolated approach to materials science where AI operates independently of other fields. In reality, the innovation behind MatterGen is likely to require interdisciplinary collaboration among materials scientists, computer scientists, and engineers, illustrating that breakthroughs often arise from the convergence of diverse expertise rather than isolated advancements. These counterintuitive points highlight the multifaceted implications of MatterGen's introduction to the field of materials science, suggesting a complex interplay between technology and traditional research practices, as well as the broader societal context in which these advancements occur. The report on Microsoft's introduction of MatterGen highlights several key aspects that may be overlooked by many readers but are significant for understanding the broader implications and potential of this technology. 1. Generative AI's role in materials discovery. While the report emphasizes that MatterGen is a generative AI model designed to discover new materials, it is crucial to recognize how generative AI fundamentally shifts the paradigm of research and development. Traditional materials science often relies on trial and error methods, a process that can be time-consuming and resource-intensive. MatterGen's ability to analyze vast amounts of data and identify potential materials means that researchers can significantly reduce the time it takes to innovate and test new compounds. Significance: this shift not only accelerates the pace of discovery but also opens up new avenues for materials that may not have been considered viable through conventional methods. The implications for industries such as renewable energy, where efficient solar cells are necessary, or environmental science, where CO2 recycling materials are critical, are profound. The ability to tailor materials to specific needs can lead to breakthroughs that address pressing global challenges. 2. Customization for specific applications. The report mentions that MatterGen can discover materials tailored to specific needs. This point is particularly important because it highlights the model's potential for customization, which can lead to highly specialized materials that meet precise criteria for performance and sustainability. Significance: customization in materials science can lead to enhanced performance in applications, resulting in more efficient products. For example, in the context of solar cells, a material specifically designed for higher energy conversion efficiency could dramatically reduce costs and improve the viability of solar energy as a mainstream power source. This capability can also influence industries like electronics, aerospace, and construction, where tailored materials can lead to innovations that enhance performance and reduce environmental impact. 3. Interdisciplinary collaboration. The report notes the involvement of researchers Tian Xie and Zhihang Liu, which underscores the collaborative nature of this project. The development of MatterGen likely required expertise from various fields, including materials science, computer science, and engineering. Significance: this interdisciplinary approach is essential in tackling complex problems. But collaboration between different domains can lead to more comprehensive solutions that incorporate diverse perspectives and expertise. As the challenges of the modern world, such as climate change and resource scarcity, become increasingly complex, the ability to collaborate across disciplines will be crucial in developing innovative solutions. 4. Public engagement and perception. The report mentions the wide dissemination of information about MatterGen across social media platforms, indicating a significant public interest. The engagement metrics, such as views and interactions on platforms like Facebook and Twitter, suggest that there is a growing awareness and curiosity about advancements in materials science driven by AI. Significance: public engagement with scientific advancements can foster a more informed populace that understands the implications of such technologies. It can also drive funding and support for research initiatives, as public interest often translates into political and financial backing. The visibility of MatterGen could inspire future generations of scientists and innovators, emphasizing the importance of materials science in addressing global challenges. 5. Potential applications beyond initial scope. While the report specifically mentions efficient solar cells and CO2 recycling materials, the capabilities of MatterGen could extend far beyond these applications. It could potentially influence a wide range of industries, including pharmaceuticals, where new drug compounds could be discovered, or nanotechnology, where novel materials could lead to advancements in various applications. Significance: the broader implications of MatterGen's technology could mean transformative changes across multiple sectors. As researchers begin to explore its capabilities, we may see unexpected applications arise, leading to innovations that were previously unimaginable. This potential for wide-ranging impact underscores the importance of investing in and exploring generative AI technologies further. 6. Long-term impact on sustainability. The focus on materials for CO2 recycling directly connects MatterGen to sustainability efforts. The urgency of addressing climate change makes the development of materials that can effectively manage carbon emissions critical. Significance: innovations in materials that facilitate carbon capture or promote sustainability can lead to significant advancements in environmental protection strategies. By enabling the creation of materials that contribute to a circular economy, MatterGen could play a pivotal role in shaping a sustainable future. The model's emphasis on efficiency and effectiveness aligns well with global sustainability goals, potentially influencing policies and practices in various industries. Conclusion: the introduction of MatterGen by Microsoft represents a significant advancement in materials discovery driven by generative AI. By focusing on customization, interdisciplinary collaboration, and public engagement, MatterGen not only promises to accelerate the discovery of new materials but also emphasizes the importance of sustainable practices and innovation across various sectors. The implications of this technology are vast, and its potential to address critical global challenges cannot be overstated. As the scientific community and industries explore the capabilities of MatterGen, it will be essential to monitor its developments and applications, as they could redefine our approach to materials science and sustainability in the coming years. 1. Generative AI in material discovery. MatterGen leverages generative artificial intelligence to transform the materials discovery process. This represents a significant shift from traditional trial-and-error methods, allowing researchers to analyze vast datasets and identify potential materials tailored to specific applications such as efficient solar cells and CO2 recycling materials. The implications of this technology extend beyond mere efficiency, potentially revolutionizing how materials are developed for various industries, leading to faster innovations and cost-effective solutions. 2. Customization of materials. One of the most valuable aspects of MatterGen is its ability to create materials that are specifically designed to meet targeted needs. By focusing on applications such as renewable energy and environmental sustainability, MatterGen facilitates the development of materials that can directly address pressing global challenges, such as climate change. This customization capability not only enhances the relevance of new materials but also aligns with industry demands for more sustainable practices. 3. Widespread engagement and public interest. The launch of MatterGen garnered significant attention across social media platforms and various media outlets. The widespread engagement indicates a strong public interest in advancements in material science and technology. This interest can lead to increased investment in research and development, collaborative efforts between academia and industry, and a greater emphasis on innovation within the materials sector. The ability to communicate complex scientific advancements effectively can inspire the next generation of researchers and entrepreneurs. For impact on future research and development, the introduction of MatterGen marks a pivotal moment in materials science, suggesting that future research and development efforts will increasingly rely on artificial intelligence to streamline processes. This shift could lead to more interdisciplinary collaborations combining expertise from materials science, computer science, and engineering. The long-term impact may result in a more agile research environment where breakthroughs can occur rapidly, significantly influencing industries such as renewable energy, nanotechnology, and computational materials science. 1. The Manhattan Project 1942–1946. This was a research and development project during World War II that produced the first nuclear weapons. It involved collaboration among scientists, engineers, and military personnel, culminating in the creation of 2 atomic bombs dropped on Hiroshima and Nagasaki. The project exemplified the integration of advanced scientific research with practical military applications, similar to how MatterGen applies AI to material discovery. 2. The Apollo Program 1961–1972, NASA's initiative to land humans on the Moon and bring them safely back to Earth, involved extensive technological advancements and material innovations. The program required the development of new materials for spacecraft life support systems and spacesuits. Reflecting a systematic and targeted approach to material science akin to MatterGen's focus on specific needs in materials discovery. 3. The Human Genome Project 1990–2003, an international scientific research project aimed at mapping all the genes of the human species. The project utilized advanced computational techniques and collaborative research to accelerate the understanding of genetic information. This parallels the way MatterGen harnesses AI to streamline the discovery of new materials, emphasizing a strategic approach to complex biological and material challenges. Future outlook: predictions for the impact of MatterGen on materials science. The introduction of MatterGen by Microsoft researchers represents a pivotal moment in the field of materials discovery and design. By leveraging generative AI, MatterGen has the potential to transform how new materials are identified and developed, particularly for applications in renewable energy, environmental sustainability, and various industrial processes. Here are several predictions regarding the future impact of MatterGen and generative AI in materials science over the next decade. 1. Accelerated materials discovery. Prediction: the time required for discovering new materials will decrease significantly, potentially by up to 80%. With MatterGen's ability to analyze vast datasets and identify promising materials rapidly, researchers can move from the traditional trial-and-error approach to a more data-driven methodology. This acceleration will enable the identification of materials suited for specific applications such as more efficient solar cells or advanced CO2 recycling systems within months instead of years. 2. Customization of materials for industry-specific applications. Prediction: industries will increasingly demand customized materials tailored to their unique requirements, leading to a surge in materials innovation. As companies recognize the potential of MatterGen, the ability to obtain materials designed for specific functionalities will become a competitive advantage. This customization could lead to breakthroughs in sectors such as aerospace, automotive, electronics, and pharmaceuticals, where specialized materials can enhance performance, reduce costs, and improve sustainability. 3. Enhanced collaboration between AI and human researchers. Prediction: the interaction between AI models and human researchers will evolve into a collaborative partnership, enhancing creativity and innovation in materials science. MatterGen will not replace human researchers but will serve as a powerful tool that complements their expertise. This synergy will enable researchers to focus on high-level problem-solving and creative thinking while the AI handles data analysis and predictive modeling. As a result, we can expect innovative approaches to emerge in materials design. 4. Expansion of open-source materials databases. Prediction: the use of generative AI will lead to the creation and expansion of open-source databases for materials research, democratizing access to information and fostering innovation. The success of MatterGen will likely encourage other organizations to share their findings and datasets openly. This collaborative environment will facilitate cross-disciplinary research, enabling academics and industry professionals to build on each other's work and accelerate materials innovation globally. 5. Environmental and sustainability innovations. Prediction: the development of eco-friendly materials will become a priority, with MatterGen playing a crucial role in identifying sustainable alternatives for traditional materials. As global awareness of environmental issues continues to rise, the demand for sustainable materials will increase. MatterGen can help researchers discover materials that minimize environmental impacts, such as biodegradable plastics, energy-efficient compounds, and CO2-absorbing materials, contributing to a more sustainable future. 6. Integration with other advanced technologies. Prediction: MatterGen will integrate with other emerging technologies such as quantum computing and blockchain to enhance materials discovery processes. The combination of generative AI with quantum computing could revolutionize materials science by simulating molecular interactions at unprecedented scales and speeds. Additionally, blockchain technology could provide a transparent and secure way to share materials data, ensuring integrity and facilitating collaboration among researchers. 7. Commercialization of AI-designed materials. Prediction: we will see a surge in the commercialization of materials developed through AI-driven processes, leading to new business models and markets. As companies begin to adopt MatterGen and similar technologies, we can expect a wave of new products and applications in the market. This commercialization will create new business opportunities, particularly for startups focused on sustainable technologies and custom materials, potentially leading to an entirely new sector within the economy. 8. Regulatory and ethical considerations. Prediction: the rise of AI in materials science will prompt discussions around regulatory frameworks and ethical considerations related to AI usage. As MatterGen and similar technologies gain prominence, regulatory bodies will need to address concerns regarding safety, intellectual property, and the ethical implications of AI-driven research. This conversation will shape the future landscape of materials science and ensure that innovations do not outpace necessary safeguards. Conclusion: the launch of MatterGen heralds a new era in materials science, characterized by accelerated discovery, enhanced customization, and a focus on sustainability. As the world grapples with pressing challenges like climate change and resource scarcity, the ability to tailor materials for specific needs will become increasingly important. The next decade will likely see significant advancements in this field. driven by the innovative capabilities of generative AI technologies like MatterGen. As researchers, industries, and policymakers navigate this landscape, the collaborative efforts will undoubtedly lead to transformative changes that benefit society as a whole.